So today I'm going to talk about extracting quantifiable time series data from biomedical images with convolutional neural networks. And this is work done with John Lagergren, who will be speaking later in the session, and Kevin Flores, who are both at North Carolina State University. Okay, so how can machine learning help mathematical modeling? So a lot of us use mathematical modeling in biological situations. So for example, one of the types of mathematical modeling that I'm most interested in is modeling the growth and spread of brain tumors in the brain. And in order to, validate these models, we need a lot of data that can be extremely expensive to obtain. So here is an example of a data set. This is from the BRATS data set, which is brain tumor segmentation data set. And you can see that there are magnetic resonance images of the brain using different types of imaging modalities. This is on the right, we have a full brain. And the goal here would be to figure out where the tumor is, right? So in this example, there may be different types of classes that you're trying to figure out. So maybe you're trying to figure out where the edema is and where the necrotic core of the tumor is. And once you're able to figure out where the tumor is, you can then use this to fit your mathematical models. And more importantly, you can use it to make individualized predictions for patients, right? So how their tumor should evolve over time and space. But as you can imagine, getting this amount of data is very difficult, right? Because what happens is if you're trying to delineate the boundaries of this brain tumor by hand, it's going to take a long time. And also, let's say you don't just have this one slice of an image, but with the magnetic resonance imaging techniques, you might have, a bunch of stacks of these images, right? Because you want to get a volume out of it. So it's not just this one image that you have to trace, it would be all of them. And so you can see how this could take a very long amount of time. However, getting this data is very necessary to be able to fit our mathematical models. Okay, so we're going to step back and start with a somewhat easier task than brain tumors. And that is going to be cell segmentation. So here's an example of cells in a movie. And each of the individual cells are, you can see they've been segmented. And as the movie goes on, each of the frames of the movie has the cell segmentation. Okay, so why do we choose cell segmentation? Well, first of all, it's a good choice because there are a lot of benchmark data sets. So this allows us to be able to compare whatever types of algorithms we would come up with actual results that other people have had. So we can see, okay, do we perform as good or better than what's currently out there? And another reason cell segmentation is a really good place to start is because there are a lot of out-of-the-box algorithms that were developed for cell segmentation. So if we are unable to come up with a great new method on our own, we can always use kind of these out-of-the-box algorithms that already exist. Okay, so what are some biological questions that we would need in order to, that we'd want all this quantifiable time series data for? So this project that I'm going to talk about started when our collaborators mentioned that they really want to understand the relationship between cell morphology and cell movement. And this is a relationship that's still very poorly understood. So what I mean by the relationship between cell morphology and cell movement is, if you have a video of a cell moving throughout time, the cell changes shape and also moves in certain directions. And so understanding if you can look at the morphology of the cell and then predict in which direction it's going to be moving. Now, as you can imagine, you need very accurate cell segmentations to be able to infer this relationship. And so what we call these are hyper-accurate segmentations. And so it's not just trying to figure out where the cells are, but you really need to be able to delineate the boundaries quite well. And also to make to understand the relationship, you actually need many fully annotated movies, which if you're doing this by hand is completely infeasible to collect, right? Because you need many, tens or hundreds of movies, all of them with hyper accurate cell segmentations, in order to be able to do this type of analysis. So this makes it almost impossible to do without some type of automated method. Okay, so we're going to start by discussing the data sets that we use. So one is one of those benchmark data sets that I mentioned earlier. So this is from the ISBI. It's a cell tracking data challenge. And these are glioblastoma cells plated. And I've played the movie here. You can see that, there's a bunch of little cells moving around. So in particular, there are 34 frames, and they're fully labeled. And each of the images has approximately 5 to 7 cells per image. The data is very clean. So there are no imperfections in the camera or any there's not much biological debris that exists. You don't have to worry about issues of focus. And this is good because it can be compared to other state-of-the-art algorithms. However, if you're trying to apply this in the real world data does not look this nice. So it lacks, natural intensity changes that real data sets might have, mechanical debris, and other types of, issues that real data sets might have. Because of this, we're also using some in-house collected data sets. So these are JR20 cells, and they're imaged in a petri dish in what our biological collaborators refer to as the regular experimental setup. And these cells exhibit biological artifacts, right? So you can see in these lower left and right hand images, these are both with the same quote unquote regular experimental setup, but you can see that the contrasting is very different. We also get a lot of debris, and the regular experimental setup also has, the experimentalists put their petri dish in, and then they adjust the focus until they think that the cells are in focus. So we also have some kind of out of focus images as well. And we have 150 labeled images here. They're usually 1 cell per image. Sometimes there are a few more. So this is like our real data set. Okay, so let's think about machine learning for image segmentation. So essentially what happens is you have an input image, you have an output target, right? So in this case, that would be the binary segmentation of the cell. And then you give all these image label pairs to a convolutional neural network, and it learns how to generate some type of segmentation. Okay, so with convolutional neural networks, I'm going to discuss one of the competing algorithms that's extremely popular. It's called UNet. And so essentially what UNet does is, this isn't super important. I'm just giving you an idea of what's going on here. So UNet basically tiles up an image, passes it through this architecture, and then the output is a probability map where every pixel in the image is given a probability that it is cell or background, and then you threshold at a certain probability where everything below that probability is background and everything above it is cell. So what's wrong with the current convolutional neural network techniques? Well, one of the issues is, as I mentioned, UNet outputs a probability map. And so this is an example of a probability map generated by one of the cells in that glioblastoma dataset. And so this white is what the actual cell boundary looks like. And the probability map is where dark blue thinks it's, the UNet thinks it's background, and the red is where UNet thinks it's cell. As you can see, in a lot of places, things are very sure. However, there is this region in the upper part of the cell for which the algorithm is unsure, right? So this is kind of almost like 50-50 area where it's like, okay, we're not quite sure whether this is cell or background. And so what happens when you threshold this is that you end up with patchy image segmentations. So on the right, this is after you have binarized the mask using a threshold, which was determined using validation. So this is a hyperparameter that's tuned with validation. It's not like we just randomly chose one to generate a poor looking image. So what happens is you can sometimes get these patchy segmentations, right? So we can see that in the upper right-hand section of the cell, this whole part is not segmented. There's also little tiny, pixels that have been selected as cell that aren't actually cell. And so if we are trying to understand the morphology of this cell, you can see that we would not be very accurate compared to the actual true morphology of the cell. So how do we address this issue of patchy segmentations? Well, we created what we call the combo method. And so basically it's a convolutional method for boundary optimization. And so what we've done is we actually, instead of considering the segmentation to be input image, output, a mask of the same size with a probability map, what we did is reimagine this as a tracing task. So the way a human segments an image, right? If someone asks you to delineate the boundaries of a cell, you're going to put a pencil on a paper and trace it out. And so essentially this is what we decided to do. So the way our convolutional network works is that we have an input image, right? So the input image to our CNN is that it's a small patch with a previously drawn contour on it. So this gives us direction to know which way we should be tracing. And the output of our CNN is the next, say, M predicted pixel locations in both the X and Y directions. So we try to figure out, is the boundary of the cell going in, in which direction? Okay, and so the reason this solves some of the previous issues is it ensures contiguity in segmented results because we're literally tracing the boundary of the cell. So we don't have to worry about having patchy regions on the interior. Another nice thing about this is it naturally provides many image label pairs. So if you look at the full image, right, there's about 8 cells in here. And an image label pair is this patch and the associated displacements in both X and Y. And so you could get tens of thousands of image label pairs per image because every single pixel along a boundary generates an image label pair for our CNN. Okay, so here's some details about training in case anyone is interested. But essentially the main thing to know is that we're actually performing a regression. This is actually a regression problem to minimize between the predicted next M pixels and the true labeled next M pixels. Okay, so now that we have this input output to our CNN, how do we actually leverage it to trace a cell in an image? So the first thing is to choose an initialization point, right? Choose something on the boundary of a cell in order to start the tracing algorithm. So we can do this in a number of ways. One is ground truth. So a user would click on the boundary of a cell. The other way we can do this is to use output from another CNN, such as UNet, which I talked a little bit about before, or mask RCNN, which is another very popular cell segmentation method. And so that's this red dot that's shown in here. Then what we do is perform an iterative algorithm using our CNN. So we take this black patch, we pass it through our CNN. Our CNN outputs the next M predicted pixel displacements in X and Y. And then we take these M predicted pixel displacements and we overlay it on top of our image. Then we move our black box and then this is passed back into our CNN. So it's an iterative method where the next M pixels are always predicted. And then when we get all the way back toward the beginning again, where we started, we use a Bresenham line to connect to the beginning of the trace. And we give this kind of buffer zone in case, our initialization point wasn't quite on the boundary of the cell. When it gets close, we just kind of close the trace. So I think this movie will explain a little bit better how the tracing algorithm works. But essentially, this is the true and the predicted image segmentations. So white is the ground truth. So obviously, when we put it through the neural network, you do not see the white boundary on there. Otherwise, this wouldn't be a very difficult problem. And the green is where our predicted cell segmentations. And so if you look here in the bottom, you can actually see where the next predicted pixels are. So if I kind of pause this right here, you can see that we're predicting the next, say, 20 or 30 pixels to at first go up and then to the left, which we can see is exactly what's going on with the cell boundary. So we are actually learning what is a cell boundary. And so you can see that at the end, the true versus predicted is pretty close. Okay, but of course, you know, eyeball norm is not the best way to judge this. So we have several accuracy evaluation metrics that we like to use. So these are pretty popular for use in cell segmentation. One is the Jacquard index, which is basically the intersection of two sets over the union of two sets. So that would look like this guy. So a Jacquard index of 1 means they are completely overlapped, and a Jacquard index of 0 means that they are completely disjoint. We also look at the Dice coefficient, which is a similar metric. And then we look at these two other metrics, the mean symmetric surface distance and the Hausdorff distance, which basically measure how close pixels are from one object to the other. So the Hausdorff distance tells us the maximum distance between a pixel on one of the sets to a pixel on the other set. Okay, so if we look at some comparison to state-of-the-art methods, this is for our JR20 data set. We have two methods because we have ground truth initializations or using another CNN as an initialization point. So this is like a fully automated method. And we can see that we get higher Jacquard scores, which means that the segmentations are better, and we have a little bit lower surface distances. So at the bottom, I've shown two, like an example image from the testing set. So the true annotations are given in green. The mask RCNN predictions are given in blue. And our method initialized with these mask RCNN predictions is given in red. And so what you can see is that, you know, mask RCNN kind of misses these small kind of protrusion, whereas our method is able to recover it. And while this may not seem super important for morphological features, this is very important if you're trying to think about the morphology of the cell. So after that, we kind of took some example data sets that our collaborators had, which were under their, you know, normal experimental conditions, but weren't similar to the ones that we trained on. And we see that the method is pretty good at being able to segment a lot of these kind of cell features. Here's another example of an out-of-sample test data set. And we can see that the method is, you know, is capturing kind of the morphological changes that are happening throughout time. Okay, but then we kind of thought about, you know, our method is actually pretty well suited towards learning from a few number of images, right? So if you think about using this type of method on, I don't know, whatever your task of interest is, you really need to have training data to do that, right? And so a lot of the methods currently used need a lot of training data. So for example, right, if we want to do like brain tumor segmentation, the Bratz data set has like thousands of images, right? But those all have to have manual segmentations on them, right? So they all have to have ground truth, someone delineate those boundaries. And so we think our method is naturally suited towards learning from a few number of images because we get so many training image label pairs per fully annotated image. And so we decided to test this using that ISBI cell tracking data set. So what we did was we used 1 image for training, 3 images, and 5 images for training. And then we also did the full data set for training. And we paired with mask RCNN trained on the same number of images. So here is looking at the Jacquard scores and the mean symmetric surface distance. as a function of the number of training images. So with Jaccard scores, higher is better. With mean symmetric surface distance, lower is better. And our combo method is in blue. Masked RCNN is given in red. And one of the interesting things that we discovered is actually our method does not really improve much beyond 5 images. So it's almost already learned everything it needs to learn to be able to make accurate predictions with only 5 labeled images. The last thing that we did was we wanted to see if our segmentations from the combo method could be used to train a masked RCNN. So what we did was we took one of our combos that was trained on 3 images, and then we predicted the rest of the data set. And then we used those generated segmentations to train a masked RCNN. And what we found was that the masked RCNN, shown in this black dashed line, it was about as accurate as training on the ground truth itself. So one of the things we really think would be useful is we can use this combo method to generate accurate training data for other machine learning methods. So here's some example results. So this is the masked RCNN trained on 3 images only. And the ground truth is in green, and the masked RCNN is in blue. And these orange arrows point to areas where masked RCNN was having trouble. So it had a couple false positives here, and then it kind of separated this one cell into multiple cells. In the middle, we show the combo method generated on, trained on 3 images, and we can see that we don't have those problems. And then this last one is when we retrained masked RCNN using the output from this combo method that was trained on only 3 images. And we see that we're able to get rid of the problems that we had in the 3-shot masked RCNN. So we're able to no longer have those false positives, and it no longer thinks that there are 2 cells here. Okay, so from all of these movies, we can actually extract morphological information as well as directional information, right? And this can be used for our mathematical models, right? So for example, we can get cell velocity and movements at given times, cell shape at a given time, or if we extend this to brain tumors, we can get the physical location of brain tumors at a given time. We can use this data for mathematical modeling, and we can also use this data for machine learning. So at the beginning, I mentioned that we wanted to connect cell morphology with cell movement. So taking a few of those hyper accurately segmented movies, what we did was we did a basic T-SNE plot, so dimensionality reduction of the cell morphology. So we looked at things like area, ratio of area to perimeter, you know, if you put an ellipse there where it's what angle is the major axis at, stuff like that. These were our features for our T-stochastic neighbor embedding. And then these colors are the different classes. So this is what direction the cells are moving in. And so we can see that we're actually kind of separating out the different directions. And if we plot what the cells look like at those various direction movements, we can see that, you know, this pink is like a direction like northeast or something. And you can see that they are, you know, it is capturing that behavior. So, so we think that there may actually be a way to predict cell movement using this cell morphology information. So in conclusion, Combo is successful at few-shot learning because it optimizes the boundary, which ensures that we have a contiguous region, but it also generates many image label pairs. We also found that we can use this combo method to generate training data for other machine learning methods, and so this can be very helpful. And for future work, we kind of want to solidify, you know, that relationship between cell morphology and cell movement, because this is all still very preliminary. And so we hope that we can get better results there. I'd like to thank my mathematical collaborators, Kevin and John, and also some of our biological collaborators. Thank you.